This video is meant to serve as a review for pHandbuffers as we move through and apply these now to biological systems. So we start our discussion about pH with the autoionization of water. We do know that water goes through a process where it does autoionize, and so here we have that reaction where we have water molecules that are breaking up just naturally into H3O plus and OH minus. So to make sure this is balanced, I'm going to stick a 2 here to show the event that's going on. So we've seen this in general chemistry. Remember that H3O plus and H plus represent the same thing, that H plus does not exist by itself, that when it's with water, that water molecule picks up that proton. And from the ionization process, we can write the Kw expression, so the ion product of water. And remember, when we're writing K expressions, these are equilibrium expressions, we write products over reactants. So we have the H3O plus and the OH minus, which are some products here in this dissociation process. And this particular expression is missing the reactants piece, and that's because the products in this case are both aqueous. So these are aqueous substances. If my pen will work here. If we put the phases in this balanced equation, and water is a liquid. Remember, with the K expressions, it's products over reactants, but you only include aqueous and gases. Okay? So pure substances do not get placed in here. And the ion dissociation constant, this value is always 1 times 10 to the minus 14. And this number is going to serve as kind of the basis for when we go through the pH scale. So what is the pH? Remember, pH is the negative log of the concentration of H3O plus. Okay. We use 14 as the basis for the scale, and that 14 comes from back here, from this expression and this exponent. We'll see more of that in a second. The pH is going to measure the acidity or the alkalinity of a substance. So is it an acid or a base? If our pH is greater than 7, it's basic or alkaline. If our pH is less than 7, then it's going to be acidic. And if the pH is 7, that substance is going to be neutral. So when we go back to this ion dissociation, or the ion product, the Kw is 1 times 10 to the negative 14. The pKw is 14. And to get the pKw, I just took the negative log of the Kw. So that's where that number for the pH scale comes from. So because the Kw is equal to the concentration of H3O plus times the concentration of OH minus, the pKw will be equal to the pH plus the pOH. And that value will be 14 because of that constant. Okay? And this is where this is coming from. This was our ion product constant, and this is our pH relationship. Why do we care about pH? Why is this important? Well, we know that as pH changes, protons can be added or removed from a molecule. As you're changing the acidity of or basicity of the environment, you're going to change the makeup of the molecule itself. And if you're changing the molecule, you're removing or adding protons, you're going to change the interactions that are present. Remember that we have intermolecular forces which are going to come into play, and those intermolecular forces are based on kind of the regions of different molecules and how they're interacting with one another. So for example, if you have a proton here, okay, we have a proton on something, if that proton is removed, maybe say it's on an oxygen, and we remove that proton, this is a substance that we can have hydrogen bonding, but if the proton is gone, then that hydrogen bonding interaction would be broken. So it will impact the types of intermolecular interactions that occur. We do know that DNA will be denatured as pH changes occur because of the interaction. And remember, with DNA, hydrogen bonding is very important because that holds the base pairs together. And then proteins will be denatured as pH changes occur. Remember, proteins are made from amino acids, and those amino acids have side chains that have certain properties associated with them. So if you start removing or adding protons onto those side chains, you're going to change the types of interactions that can occur. So this is just showing kind of the removal of a proton here. This is guanine, which is one of the base pairs. And so in DNA, these base pairs, you would have this substance hydrogen bonded to another. And the hydrogen bonding, you could see we have regions here where hydrogen bonding could occur. And so if this goes through a process where we're removing a proton, you now are missing a hydrogen on there. So that's going to disrupt the hydrogen bonding that can occur. For guanine, this happens at a pKa of 9.7. We're going to see the relationship between pKa and pH here in a second, but what this means is that if you're getting your pH around 9 or around 9.7, you're going to have this proton removed. So it's very important to maintain a certain pH in biological systems so you don't have this happening. And the way that we do that is through the use of buffers. So a buffer will help maintain the pH of a system. Buffers are made from a weak acid and their conjugate base. They can be described in terms of their capacity, buffer capacity, and range. The capacity, this is just describing how much of the acid or base can be added before we start to see pH changes occur. So with a buffer, it's supposed to keep the pH change constant. Again, it does that because you have an acid component. I'm going to put that in water. And this is just showing the equation that's written from this. So when you make a buffer, you actually put both the acid and the conjugate base component in there to start with. And so if you add acid to your system, it's going to react with the base component. If you add a base, it's going to react with the acid component to essentially neutralize that out and produce water. So it's able to absorb some pH change. But there is some limit to how much this can do. This can operate, and so that's referring to the capacity. In terms of the range, this is the pH range over which the buffer will be effective. Okay, so you pick a particular buffer system, what pH will it maintain, and to what extent will it be effective? Now in general, buffers will work best when the concentration of components are high and when the concentration of the components are close to equal to one another. And when I say concentration of components, remember, I mean that weak acid and the conjugate base, these components. They're also going to work best when the pH, or the desired pH, is within plus or minus 1 unit of the acid's pKa. Okay? So this really is more related to this range here. The pH is effective within plus or minus 1 unit of the pKa. What that means is if you are trying to create a buffer system at a certain pH, you are going to choose an acid whose pKa is within 1 unit on either side of the pH that you want. So not all buffer systems work at all pHs. Just some examples of buffers. Phosphoric acid is an important biological buffer. And so phosphoric acid, H3PO4, written here, this is a polyprotic acid, and so you have a number of protons that can be removed, a number of hydrogens that can come off, and this is showing the complete dissociation or removal of those hydrogens. And with each proton being removed, there's a certain pKa associated with that. In general chemistry, we talked about the Ka associated with the removal of each proton. Here we're just converting that to the pKa by taking the negative log of the Ka. So pKa is negative log of Ka. And remember, the Kas of different acids These can be found in an appendix. So if you've held on to your general chemistry book, they're in there, and you can look these up online as well. So there is a pKa associated with each of these values, or each of these processes, and you'll see that underneath here. The first proton comes off around 2.12, the second around 7.21, and the third around 12.67. So physiological pH is around 7.4. So if the physiological pH is around 7.4, that means that we are looking at this particular portion of the reaction. Okay, so we're in here. And we know that because this pKa is within plus or minus 1 unit of that 7.4. This is not, nor is this. So here is where we're focusing on. This is the buffer system that's existing at physiological pH. So remember, with buffers, we use the Henderson-Hasselbalch equation, and this says that the pH is equal to the pKa plus the log of the concentration of conjugate base over conjugate acid. And that's the Henderson-Hasselbalch equation. So we will, especially in lab, look at situations where we're calculating pH and pKa, or we're trying to prepare buffers and pick the best concentrations for buffers, or monitor how changing these concentrations will impact the effectiveness of our buffer. So some other important biological buffers, we have the carbonic acid bicarbonate buffer, and here's the equation for that. We have the phosphate buffer, which we just saw. And then there are protein buffers. And the protein buffers will involve amino acids. So when we start to look at amino acid structure and talk about how proteins are going to fold, we will look in more detail at how pH is going to impact the reactivity of those side chains on the amino acids. But this video is just serving as an overview, kind of review of what pH and buffers are and why we care about them in biochemistry.